me show you how to be a good breezy and change your predictions.
Actually, can you tell us, can you define, introduce DADVI to
Yes,
listeners,
sure.
I would say, I was surprised you didn't. So there's two blog posts, at least we'll put into the show notes. One that's on your website and another one that you wrote for PyMC Express. I am very surprised that one of them is not called, Who is Your DADVI Now? Because that would have been
That's
perfect,
good.
but next one.
Yeah, that would have been a better title. Yeah, next time I have to consult you for title tips.
Please do.
Not sure, yeah, that JMLR would have appreciated that. Well, you never know, but it's a good one. Yeah, I guess, the starting point was a little bit that, so I think I mentioned briefly before that, right? Like I worked with Stan at the time. I kind of got to PyMC a bit later, but I started out using Stan more, and I built this like tennis prediction model, and it was just a bit slow, And part of it is like, I think now I look back, like there are ways of writing these models more efficiently, right? There's kind of an art a little bit also to like how to write your like PyMC or Stan program, right? Which I think at first maybe you don't really appreciate, right? There are like these little tricks. Anyway, but like it was a little slow, and so I wanted to do something fast. And then in my PhD, I started looking at like approximate inference methods, And there's kind of different kinds of them. Like there's like basically there's stuff that's like tailored towards particular problems, right? Like if you do state space modeling, you might use a Kalman filter, some variant thereof, right? If you do Gaussian process modeling, you might use some like tailored variational approximations, and there'll be packages for that and stuff. So I was kind of using those, but like I guess what would be really nice, right, is like if you had your probabilistic program, right, your like Stan or PyMC code, and you could just fit that thing more quickly, right, without like actually having to worry about, okay, I'm now in like state space land. Can I frame my problem as like a Kalman filter, right? And like, then how do I do that, right? Can I still automate parts of it, right? Like, but I have to put some work into it, and that's kind of a shame, right? Because like part of the fun is that you can just do whatever you want, well, to some extent, right, with programming languages. So at the time when I was doing my PhD, yeah, there was already ADVI that came out. So that's automatic differentiation, variational inference, right? And that is just, the promise of it is really cool because like it's basically black box variational inference. So the idea is like you actually do nothing different from the way you do anyway when you write PyMC or Stan, but you can run this variational inference algorithm, and it should be much faster, and it should give you, at least the promise is kind of, you should have good mean estimates, but the variance estimates maybe might not be that great. But I don't know what your experience is, but often when I fit these models with MCMC, like at the end of the day, I kind of just care about the means, and I like having the variances sometimes too, but for some problems even the means are not bad, right? If I could just get the marginal means, right, and like ideally good variances, that already goes quite far. Like the thing is, like, actually when you fit MCMC, it's kind of bananas that like you get all of the correlations, right? It's a very powerful thing, right? You get all the posterior covariance, right? All the correlations should be sampled as they are, which is really cool. But like practically a lot of the time, I think if you just had marginal means and variances, that would already be pretty cool. And actually slight tangent, but I think like, INLA, right, is quite popular, and INLA I think only does marginals most of the time. So I might be misrepresenting that, but it's like, these basically a lot of the time that's good, right? So it's like, oh man, that's cool, ADVI's here. But the thing is, like, when you talk to people who've tried it, usually my impression was that they often ended up a bit disillusioned, because like, and one big problem with ADVI is that like it's just fiddly, so like you specify your model, you run ADVI, and then actually the problems are a bit different in Stan and PyMC. Like in Stan, I think they have some kind of tuning window where like at the start they try to set the parameters. So I should say ADVI has like a stochastic objective. So like it's at each step you basically get like a noisy estimate of what it's trying to optimize. And that means you're in stochastic optimization land, which means like you have to use something like, Adam or AdaGrad or whatever, right? One of these stochastic optimizers. And they need a step size. And so you have to tune the step size, right? And they don't have like a convergence flag. So you have to somehow like work out when things are converged. And in Stan, yeah, they try to tune it at the start, and then they have some kind of criterion where it's supposed to try to flag when it's converged. but a lot of the times it doesn't get it right, and it terminates too early, or like it gets its tuning a little bit wrong at the start, and it doesn't find a good optimum. And it's also not super repeatable, right? Like it's because it's stochastic, so sometimes you get different answers if you run it multiple times. So, and in PyMC, it's maybe a slightly different problem. Like basically, I think it sets like a quite a conservative small step size, which is usually small enough, but then it doesn't really, the convergence criterion rarely triggers. So like if you actually run it, you don't really know how long. And that to me, right, it kind of defeats the purpose a little bit, because then it's like, yeah, you have this supposedly faster method, but now you have to babysit it, right? And you have to check your step size. You have to look at like convergence plots. It's like, well, I mean, maybe for some huge problems you're willing to do that, right? But like generally, it's just a bit fiddy. And then at the end, even if it's converged, right, you're not sure whether the estimates are that great, right? So that's why when I was doing my PhD, I wasn't really that into. I didn't use ADVI that much, because I kind of stayed away from it, because it's like, yeah, I thought, oh, maybe it's just too good to be true, right? Like you just can't get these like fast approximate methods without sacrificing some of the generality, right? Where they're saying like, okay, I'm gonna fit a GP, I'm gonna pick the GP approximation, So that's kind of where I was at. And then in 2020, I went to a conference, and I saw a talk by Ryan Giordano, and he's like a super smart guy. Like, I mean, I was so impressed because like he did this like talk on some bridging between frequentism and Bayesianism. Like, I guess that their group, like it's Ryan Jordan and Tamara Broderick and the group, like they're just like really, they've just read a lot of stuff, and they're equally comfortable, I think, with like frequentism and like Bayesian stats, and they actually like put them together to form some kind of improved version, which is kind of cool. So I was like, oh, this is a cool guy. So I chatted with him a bit, and then he told me that somehow we got on the topic of ADVI, because I'd done some other version of variational inference anyway. But yeah, and he said, oh, well, I did this for a previous paper, and I just fixed the draws. So in ADVI, right, you have this estimator, and you pick a new draw every step. And he said, well, I just took like, some set, I think it was maybe 60 or something of draws at the start, and then I just used those rather than drawing something new every time. And it worked fine, And I was like, oh, that's cool, So I'll give that a go. So I tried it, and sure enough, like it seemed to work well. I wrote up a little blog post at the time. It's on my blog still, and I had some questions, so I sent them to Ryan, and then that's kind of, we both kind of thought, oh man, this is kind of cool. It's working quite well, and it'd be nice for to share this a bit and see if it's useful for other people. So that's kind of how the paper got started, and yeah, I guess I should say how it works, but.
Yeah, I mean,
Yeah,
that's a great, I think that's awesome, because that gives us a great background about, like why you were using that, what this is about, and what the problems are. And then, like, probably now you can tell us a bit more about, the intuition into how that works. Because in your blog post, I think it's really well done. Actually, if you have your blog post, you can share your screen, because I think you have this great plot, where you show in-field variational inference in red and the bivariate Gaussian in blue, and you're showing that we can get, like, for a simple multivariate normal, 2D multivariate normal, you can get the mean pretty accurately, but then of course the covariance, you don't get it, because ADVI is based on the fact that each parameter is approximated by a standard normal. And so, yeah, I think this is great. And then you'll be, so yeah, let's start with that, and then we'll take it from there.
No, yeah, that's exactly right. Yeah, so I guess this is really the key takeaway with mean field variational inference, that like certainly for like if your like target posterior is like multivariate Gaussian, like even if it's really correlated, it will find the right means. But yeah, it will avoid like, so basically the objective function that's used is called like Leibler divergence, and it's also one particular way around. So it's the Leibler divergence between this approximation, right, which is this like factorized Gaussian thing, and the true posterior. And it turns out, so it actually ends up being a sum of two terms. So it tries to like maximize the entropy of your approximation. So that'll try to make it like spread out as possible. But it also tries to maximize the expected log posterior. So kind of like basically tries to find the mode. So it's a bit like kind of a regularized map estimate in a way. So it's gonna like try to seek the mode and it's gonna try to expand, but it really tries to stay away from like low density regions. So that's why you kind of get this picture where like it kind of finds the like, part that has high posterior mass, but it will miss, all of this part. And it will underestimate the variance as a result, right? Because you can see that this axis, right, it should be all the way over here, so that's kind of the price you pay.
Yeah, exactly. So, but as you were saying, sometimes this is perfectly fine, and you don't have to necessarily have a good idea of what the posterior covariation is. But in a lot of cases, you also do. So that's a problem. And so, yeah, maybe can you tell us, well, what do we do then? Like, if you can't use nuts, but you still care about the covariance, what do you do? Because there seems to be a problem with the black box method that there is already in PrimeC, the ADVI method.
Yeah.
And so, yeah, what's the problem here and how can we solve it?
Yeah, exactly. Yeah, so I mean, that's the other thing. So I already mentioned, right, that with ADVI, ideally it should give you this answer, right? But it doesn't even really give you this answer is the problem a lot of the time, right? Or it's hard to get it to get to this answer. So the first thing that DADVI kind of does is that like it pretty reliably gives you that answer. So like you fix the number of draws that you use, and that introduces a little bit of like noise because you're like, really you should use infinite number of draws to get the perfect result. So it won't exactly get this mean right. Actually, pretty sure I fit this with DADVI. So it's like I just took like, this correlated a Gaussian, and then I fit DADVI. So you can see it gets it pretty much right. Obviously, this is a toy example, but generally it's pretty close. But yeah, so it gets, let's say it gets the means right, which it will in a fair few cases. Then you still have the problem that you don't have the correct marginal variances and you don't have the correlation, like you say. So that's where there is this other thing that comes in that you can do with DADVI called linear response. So there the idea is that if you have good means and you can differentiate, there's this kind of cool identity that you can derive called a linear response that then gives you the covariance. So I guess it's kind of a little bit magical, I guess. I mean, I thought so anyway. So this is something that Ryan worked on a lot, so he really brought this. But like, yeah, there's this relationship. I mean, I guess intuitively kind of it's like you have your means and you perturb them a little bit. And I guess how they shift basically ends up being the covariance. And it turns out, yeah, if you find the exact optimum, which again, you don't do with ADVI, right? With ADVI, you find the exact optimum of this like deterministic objective. Then you can do this trick of like looking how would the means shift if I prod this thing a little bit, and that gives you the covariance. So you can actually recover this covariance, and if the means are right, then the covariance will be right too. So actually, the variances can be as wrong as you want. It is all just about the finding the means. Yeah. That's kind of a neat result.
Yeah. And so can you actually talk about that linear response? Because, yeah, so the one common critique of ADVI, especially mean field ADVI, is its tendency to underestimate posterior uncertainty, as we've just showed. So DADVI is claimed to help with more reliable covariance estimates via this linear response. Can you explain how that works and whether it fully resolves the under-dispersion issue?
Yeah, that's a really good question. So, I mean, so as I mentioned, right, like if the means are right, then it will get it right, but there are some caveats. So one caveat is that it involves the inverse of the Hessian of the objective. And the Hessian for this mean field objective, it'll have like 2 times the number of parameters of your model. So you have to invert something kind of big, right? The thing though is it's not as bad as you might think because, and this is also something, I mean, Ryan pointed out at the time that like basically you can often you don't need the full covariance, right? Again, like you might be interested in for example, one parameter, and then you can do something called conjugate gradients to like if you just have this thing called the Hessian vector product. So like the Hessian times a vector. There's this well-known, right, like linear algebra technique called conjugate gradients, which will allow you to solve for like a particular parameter. And even actually, you can have a function of your parameters as well. So if you have a function of your parameters and it's nonlinear, you can do something called the delta method. That's how you derive it, like basically Taylor expand that thing. And then you can also do that with a Hessian vector product, with this conjugate gradient trick, because it's just kind of changes a little bit. So basically, yeah, so yeah, caveat is, right, it involves this negative Hessian. However, like if you only care about certain functions of your posterior, which is often the case, then you can do the CG trick to get it kind of quick. Caveat 2 is that this is how it hopefully works, right? It finds the means. In my experience, that doesn't always happen. And I haven't really formalized this, but intuitively kind of imagine, you can start thinking about curved stuff, imagine some kind of banana here or something, right? Like a banana with equal posterior density everywhere, kind of. Then this thing, it might, or I guess even worse, like a banana with a bit more weight in one corner, then this thing will seek out that bit, right? And it'll kind of ignore the other bit. And at that point, you don't get the mean right. And so your covariance will also not be correct, I guess. It'll probably be an improvement because it kind of, explores things a bit more. But yeah, so that's the caveat number 2, that if you have a complex model, and I think it mostly comes down to competing explanations, like Gaussian processes, for example, sometimes you have I think you could have 2 kind of distinct length scale settings that would make sense, but they only make sense if some other parameter also varies together, I don't know, maybe you could imagine something where there's a strong seasonal, you could explain something with a strong seasonal pattern, but also maybe it's just, some transient thing, there's a way of explaining it as noise or something, and then there's kind of these 2 competing things. And then I think if it gets if the hyperparameters start interacting with the other parameters, potentially you get some kind of curved thing, and then yeah, I'm not sure. However, I will add, so I'm not sure that it could be that even in those kinds of cases, you might actually end up with quite a predictive model, because it will seek kind of the highest density part of the posterior, and potentially, right, that's perfectly fine if you predict, right? If you're for example, you care about prediction, maybe that's actually going to work. So yeah, I guess that's just a caution, and I would say that if you suspect that your posterior is kind of nonlinear and difficult, then maybe this will kind of still not explore all of it, if that makes sense.
Yeah, it makes a ton of sense. And we've given actually some tips to. I think you can stop sharing your screen, by the way, now,
Yeah,
and unless you wanna keep
all good.
sharing that. But and yeah, so in episode 142 with Gabriel Stechschulte, we gave some tips, folks, to work with approximation inferences and try and see and understand when they are reliable or not. So I recommend listening to that one if you want more details. Staying on ADVI, so if I understood correctly from the blog post you wrote, the original ADVI relies on stochastic gradient optimization, whereas DADVI optimizes a deterministic surrogate. So what's that about? What does that mean? What are the trade-offs? Whether that's in terms of robustness, convergence diagnostics, sensitivity, stuff like that.
Right. Yeah, exactly. So ADVI has this stochastic objective. So it basically, the ADVI paper derives this estimator of this Kullback-Leibler divergence, right? We already talked about that that's the kind of measure that you try to minimize with the method. So it derives this estimator, but so it's an estimator, right? So it, for any draw, basically you give it a draw of actually from a standard normal, and then it will give you a noisy estimate of both the scale divergence and also its gradient. And yeah, and that means you're in stochastic optimization world. But the nice thing about it is that those draws are kind of fresh, right? So you make a fresh draw at each step, and eventually you do have guarantees from stochastic optimization that it should kind of find the optimum, right? It's just that in practice it can be a bit fiddly. On the other hand, so what DADVI does, right, is it takes that estimator, and it just takes a set of fixed draws. So instead of taking a new one every step, you fix typically it's actually 30 works well. And so that means you don't have the noise, right? You don't have a new draw at each step. So the noisy part completely disappears. That noise disappears. But you do have like a kind of a sample, like an error from that sample, right? Because you picked these 30 draws. If you picked 1,000, right, you would have less. Basically, you take the expectation, right, of this Kalbeck-Leibler estimator, and like the more draws you get, the sharper that thing will get, right? So if you truncate it at 30, it's a bit fuzzy. So yeah, and so that means, but it means, right, that like, so one is stochastic optimization and the other is more sort of standard optimization, which is nice because then maybe if you worked with like SciPy and stuff, right, you can use the SciPy has this minimize function, and there's all these like optimizers in there, LBFGS, BFGS, Hessian, like Newton Trust, whatever, right? So you can use any of those, and you can pass not just the gradient, but you can also pass the Hessian vector product for it to be like super reliable, which is what we actually do. So yeah, you basically all the convergence issues go away. I'm maybe sounds bold, but I think that's pretty much the case. So like you don't have to worry about the convergence so much. Like, sometimes it takes a while to converge because like it kind of gets it really right, until the like gradient norm is like 0 and stuff. But yeah, the convergence worries go away. But you might worry about what you pay in terms of bias from this like sample. So you do introduce a little bit of noise from that, but it tends to be quite small. So in the blog post, I think I show like a comparison, and at least empirically from all the experiments I've run, it's quite a small amount of scatter that it introduces. So that's not really such a big deal. And yeah, so I mean, I guess another thing to say there is that like another thing it does cost you is that you can no longer do full rank. So in ADVI, you also have the option of like fitting a full multivariate normal for across all your parameters. You kind of lose that by truncating the draws.
Let me show you how to be a good bee.